الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولى و نعم النصير. Today we will start our chapter 2 on motion description. In this chapter we will study the 3D motion of different objects in space like an airplane and or maybe a shuttle. We are focusing on the 3D position and orientation of a rigid body in space with this content. Let me first start with distinguishing some robot components and defining the links and the joints, especially the primary links and joints that a robot consists of. Then we will go to some part of serial and parallel kinematic structure as the basis of our robotic manipulation design. Later we will talk about spatial motion description, the coordinate system, different representation for position and orientation, and then a general motion of the rigid body, and finally with homogeneous transformation. I hope that we can cover the whole chapter in 2 sessions. Let's start with robot components. A robot mechanically is designed based on joints and links. The joints are the part of the robot that the links can move or rotate about it, or it can translate along it. We will show different joints. And the links will provide us with the reachable workspace. So consider our hand. This is a very, very fantastic design. We have different kind of joints. For example, at the shoulder, we have a rotational in 3 degrees of freedom. In our elbow, we have 2 degrees of motion, extension and flexion, and also rotation around this. And we have also 3 degrees of freedom in our wrist motion. But the links and joints both can be rigid or flexible. Let me show you some flexible links as well. As you see here, we have only one link and one joint. The joint is rotational and the link is very tall and thin. That makes it somehow flexible joint. And flexibility provides us with some benefits. We are using the flexibility in many applications. But in terms of analysis, it provides us with some complexity. So right now we limit ourselves to rigid links instead of flexible link. So we consider both the joints and links to be rigid. Later in the future chapters, we talk about some flexibility in joints and in links. Regarding the joints, we have 2 types of the joints. The first part are primary joints, the basic joints, and the most important one in terms of analysis. These joints have provide the links, the connecting links, only 1 degree of freedom. And if the degree of freedom is rotary, we call it a revolute joint, like motion in just revolute motion in the space. So as you see, we have a base and a follower. The follower can move around the base about an axis of direction, which is, we call it the axis of rotation here. And it is only 1 degree of freedom. So you have only 1 degree of freedom here. Another primary joint, which is also very important, is prismatic, or prismatic, we call it prismatic and denote it with P joint. This has also 1 degree of freedom, but there is an axis of motion for the follower, But as you see, the motion is translational. It is not rotational. And by adding these joints together, we can have another structure. We call them primary joints because they are the binary joints or the basic joint. If we have some more sophisticated joint, we can replace them with these primary joints. Let me also call some compound joints. I appreciate if all the people please mute their microphone and more easily together. Of course, I appreciate if there is any question or any interruption, please just raise your hand and start talking with your microphone. That would be much of appreciation from me. Here, I provide some compound joints. These joints have more than 1 degree of freedom. And in just one simple connection, as you see here, we call it universal joint, and denoted with U. We have 2 degrees of freedom. Both degrees of freedom are R, rotational. So 2 degrees of freedom in 2 directions. Usually these 2 directions are perpendicular to each other, but it could be also not. But usually in the design, in the mechanical design that we have 2 perpendicular joints. Why we call this a compound joint, not a primary joint? Although mechanically it is 1 joint, but in terms of kinematic, we can consider that as 2 rotational joints. Just keep it in mind. Both of them are on one single point. They are compound on a single point. It is not possible to put 2 different joints on one single mechanically, but kinematically it is quite possible. And this is why we call them compound joint. So it has 2 degrees of freedom. We can represent a U joint or a universal joint by 2 rotational primary joint. The same will go with cylindrical joint. The cylindrical joint has also 2 degrees of freedom, but 1 degree of freedom is translational, like the prismatic joint, and one of them is rotational. So it can rotate and it can also translate along an axis. And as you see, the axis of rotation and translation is the same here. So the cylindrical joint has also 2 degrees of freedom, but it can be replaced or considered as 2 primary joint, RP joint, which both of the axes of rotation and translation is the same. And finally, we call a spherical joint, ball and socket joint. It is very interesting. You have a semisphere, and a socket that it has compounded. With this joint, we have 3 degrees of freedom. We can have rotational along all different axes of rotation. But as you see, these 3 joints, spherical joint, is very, very commonly used in many, many mechanical structure. Also, universal joint is used in automobiles quite naturally and quite frequently. But in mechanical structure, usually, especially in serial robotic analysis, we can replace a spherical joint with 3 intersecting rotational joints. That's why our primary joints are of most important, and we consider them as the basic components of a robotic manipulator. Of course, there are some other type of joints that I'm not discussing it right now here, but usually there are a compound of 2-3 other primary joints, as you see here. After having some joints and links in mind, the links are quite easy. There are some connecting the joints. They could be just a single planar link, or it could be somehow twisted and with offset and so forth. We will see a number of them here. So, considering the primary joints and links, and all of them considering it to be rigid, no flexibility in them, we can put them together to provide some kinematic structure. The kinematic structure is how these joints and links are connected together and which one of them are actuated. So we are calling a mechanism or a kinematic structure just by different arrangement of links and joints. Here, I provide two very commonly seen mechanisms with some movies here. The first one, as you see here, let me first describe it and then play to see how this is working. This is a crank and piston, very simple crank and piston mechanism which is used in many automobiles and many other mechanisms, as you see. The usual version is that we have, let's say, crankshaft, one single link here. So we have a rotary joint here. Everything is in a planar, so we have a planar case now, both of them. Just in all the motion is in a plane, not out of the plane. So we have one single joint here, rotary, one single joint here, the second one single rotary joint here, which also provides some motion here, and a prismatic joint here. So we have a mechanism designed by P structure. We call it P structure. This is a single kinematic loop. I will explain it a bit later. But also we underline something here. The joint that has been actuated, we underline it here like this. So it has four joints here, P structure. But only it is enough to actuate just one single joint. It could be the R1, as you see here. We can put a motor here and then replace or change or transmit it to a translational motion here. It is also called a cinematic loop, a single kinematic loop. A single kinematic loop, if you see we have a base, so this is put on a base, and this part is also on a base. If you just, again, consider the mechanical structure here, the joint and the links, this joint is on the base, so we have a link, we call it base, one joint, another link, link 2, another joint, joint 2, another link, link 3, another joint, joint 3, another link, link 4, and another joint, the prismatic one. So we have a 4-bar mechanism or 4-link mechanism which introduce a single loop. So if it is in a loop, if it is not open, consider if it was open, it doesn't have any limitation or constraint there. We don't have any prismatic joint here. It will be an open chain or a open kinematic chain. But this is a closed cinematic chain, but only one single loop. We have one single kinematic loop. And if we introduce that into the robotic, we can just use, since it is one single kinematic loop, we can use only one actuator to move the system around. And let's see if this is moving. You see, we are rotating here with a motor, and we are getting a prismatic, go forth and back prismatic translational motion. Let me also see here, we have some similar to this, but somehow different in the structure, as you see. Here, we are seeing again another R, which is actuated, another rotational motion. Again, everything is in a plane. So we have a single motion here. But this motion will provide us, so we have another rotational joint here to have this motion rotational, but this rotational is, unlike this one, is connected to the link with a prismatic joint, it provides a translational joint. And also the last part is also a prismatic joint. We call it RRPP. If it is in a plane, it is quite easy to generate some structure like that, and not mechanically, but kinematically. You can see that we have a rotational, another rotational, a translational, a P, and another translational here. And if we are actuating the rotational part, we underline this R here. And you see again that this also provides, this is also giving a rotational motion to a translational motion, but quite different than that. If you see the motion, it is in this part, it is slower. At the end, it is much faster. And it is very common to use something like that as a mechanism that we can use in our different structure. We can call them mechanism, we can call them robot, but it is not that important. There are a bit of difference here, but the thing is both of them provide a single kinematic loop. We have a base and 4 links. This is a 4 link or 4 bar mechanism, but with different joints. We understood here with these 2 examples that the joints and the orientation and the connection that we have the joints are so important. Here, there is another mechanism which is quite interesting. It goes, it traverses a linear path in the space. But as you see, we have more joints and links. It is not just 4 long joint or link. As you see, we have a base and 1 joint here, 1 here, 1 here, 1 here, 1 here, 1 here. And then some connecting links. But the connecting links provide not just single loop, but provide us a number of loops. You see, you have a loop here, you have a loop here, and you have a loop here. At least 3 loops are here, as you've seen. The loops of, or the chain of joints and link which are connecting to each other. Everything is again planar, and we can see that this mechanism has again 1 degree of freedom. You can put only a motor here. Of course, you can put a motor here as well, but it is not important. You can put a motor here, and then by moving it around, you can have a translational motion, as you see. Of course, it doesn't have a very long workspace, and the motor cannot rotate all over again because we have these kinematic loops, and these kinematic loops provide some constraint in here. Okay. Up to here, we understood how the links and joint can be connected and how the kinematic loop provide us with different structures. Let me also show you some kinematic loops which are out of the plane. We call it spatial kinematic loop. This is also 1 single kinematic loop, very single. So with 1 single kinematic loop, we can use only 1 motor or 1 eye actuator to provide this action. But this action or this motion is not just in a plane. It could be out of the plane. And it is very interesting to see. You can have a twisting plate here, as you see, with this mechanism. The important difference here, here again we have a rotational motion, basically 1 R here, another R here, another R here. Let me stop it. Sorry. It doesn't want to stop. But as you see, the joints are not perpendicular to each other. They have some angles and offsets. And with adding some angles, the twist angles, and some offset, we can have some out-of-the-plane kinematic chain. Of course, all of them provide different structure, but unfortunately, in this course, we cannot basically analyze all of them, and we will analyze only the most simple one, which is seen in this structure. In this structure, we call it open kinematic chain. So the difference between this mechanism and the other one is that the end effector or the end link is not connected to the base or not providing a single kinematic loop. There is no loop. The loop is open. It is open kinematic chain. So as you see here, many robots that we showed in previous session as well are composed from a single or a number of links and joints. You can see we have link 0, link 1, link 2, link 3, 4, 5, 6, 7. And different joints, the joints are how they are rotating. As you see, we call the joint, we can show the joint with the axis of rotation. For example, this joint has an axis and a perpendicular axis of rotation in z direction, so it can move out of the plane. But this joint is in the plane of here, as you see this one usually as well. And in many robotic design, we have a RRR structure, but not a RRR in a plane, but RRR in out of the plane and the spatial case. As you see again, for this motion, we move from outside the plane like this, and the other two joints provide us reaching to different points. So we can move the base, and then we can reach to different points. So these 3 degrees of freedom can provide us a reachable point x, y, z to the point that we will want to reach, or to the task space that we call. But these 3 are not usually enough, because we also need some more degrees of freedom for orientation. It is not quite enough to reach to a point. It is important how to reach to a point. Consider that you want to write on a blackboard. You should reach to the blackboard, but your hand should be somehow oriented perpendicular to the blackboard that you can write. If your hand is not perpendicular and has some angle, you cannot write quite easily. So we need some degrees of motion in terms of rotational axis. And this rotational motion can be provided with a spherical joint, but spherical joint is very hard to actuate. We usually use 3 single rotational joints that are perpendicular to each other somehow and are interconnecting or intersecting at a single point. And as you see here, there are 3 joints here, 1, 2, 3 joints that are somehow connected in these 3. The joint axis 5 and 6 here intercept, and then we have an axis 7. And why we are using another axis, as I mentioned to you before, we could have some redundancy, we can have some more degree of freedom to have better motion in the design. But in terms of typical categorizing the system, this is a single open kinematic chain. We have only one kinematic chain. There is no other loops. And it is open. And we call this serial manipulator or serial robot. And our course is focused on serial manipulators. So the issue that we can say, these are 2 different type of components. We have 2 different kind of structure. Of course, we can integrate both of them together and have a hybrid structure. Some part of it could be serial and some part of it could be parallel, and we can use that in here. To understand and analyze all the details of this robot structures, we need to have at least 2 courses. One course is this semester, which is more introductory in terms of the open kinematic chains, and one more another course in parallel robot, which is mostly interesting in terms of having some compound structure. So let me introduce a number of serial robots that we are working with, not in terms of the application, but in terms of kinematic structure. Here we call a RR component. As you see RR, we underline both of them. It means that we have two rotational joints and two links, of course, and one base, and it is an open case, but we are actuating both of them. We are using two motors here. So we have 2 degrees of freedom and two motors or two actuators. So in terms of looking into the joints, we see that we have two motion, theta 1 and theta 2. We can have two motors here. And in terms of the final destination that it can get, the robot can get into a XY position. So we can have XE and YE, the X and Y of the end effector as the final reachable workspace of this robot. 2 degrees of freedom in terms of two motors or two rotational joints, and 2 degrees of freedom in terms of what we can get out of the robot. We call it a fully actuated robot. We have 2 degrees of freedom and two actuators. We can have the same thing in plane with adding another joint here. Why we should add another joint in space? We cannot have more than X and Y in space. Yes, we can. As I mentioned, in a plane, we can have X and Y and also a phi or a theta, the angle that the robot is performing in the space. Not only the reachable point at the end effector is important, how it is reached here, we call it the orientation. And now you are quite ready to learn more about how we should represent the orientation. Of course, in a single plane, the orientation is represented by a single angle, a theta, but in a space, it is more sophisticated, and we would like to see that how we can, for example, represent the angular motion of an airplane or a missile or a shuttle or the end effector of a robot in a space. But these are simple. RR manipulator, almost in all the section that we have. We start with this single and simple manipulator. I can say that in many chapters we call this 3R or RRR manipulator. We will consider that and analyze that in more different depth. But there are some more different structures. In a plane case, we can integrate some prismatic joint and rotary joint. Here you see PRR. We have again 3 degrees of freedom in terms of actuation, but this first actuation is not a single motor. It should be a translational actuator. It could be a linear motor or it could be a hydraulic cylinder to actuate that. We are not working on the actuators now. We are thinking about how the kinematic structure is represented. And as you see, we are talking about a PRR. You see PRR, and we should see that how this is, and it is providing again X, Y, and theta to us, but in a different way. And it might be better than the previous structure for some application or not. Another very interesting application, which is quite fast robot, could be PRP actuator. As you see, PRP actuator. PRP actuator again provide you with 3 degrees of freedom. Since we have 3 motors, 3 degrees of actuation, we have also 3 degrees of final motion, which is X, Y, theta. And we cannot have more than that in a robot, in a plane. So if we add another joint here, for example, another motor here, we could have, or here, or in previous one, instead of 3R, we add another 4R.
if we put another actuation, it doesn't provide us with another degrees of extra degrees of motion here. We cannot have x, y, theta, and another theta or phi, because in a plane there is only 3 degrees of freedom. But we are redundant in terms of actuation. We have more freedom how to move, and we will talk about that in redundant manipulators. So let's also look into 2 other spatial serial robots. 2 most important one maybe. The one here, which is called Scara, I showed you. This is very, very interesting in terms of pick and place motion, quite fast. It can go to 90 pick per minute. Of course, the closed loop kinematic chain can easily beat this structure and go to 120 pick per minute. But the structure they have, as you see, they have a rotation here, again out of the plane. But instead of having an in-plane like this, we have 2 motion perpendicular to the gravity. And this help us to have the weight of the robot is not basically providing some resistance to the motion, so we can have faster motion. This structure, in terms of mechanical design, can provide quite fast. So we have an R here, as you see, an R here, another R here, 3 RR, and to go and pick something or place it something else, we have a prismatic joint. So we have a RRRP structure. We call it Scara. Of course, we can have different RRRPs depending on the direction that these rotational axes are compound to each other. But Scara has some sort of RRRP in this kind of structure. Again, it is an open kinematic chain, and it is out of plane, simplest, maybe the most simple, not the most simple, but maybe one important single structure. We will work on the Scara robot as well in many, many things in terms of the chapters that come forward. And finally, the last but not the least, is the usual 6R manipulator. I didn't put R here. I put it 6R here. It seems that it is a general manipulator with 6 degrees of freedom, all rotational. Puma is maybe the first industrial part, but now there is no Puma anymore. There are more other brand of robots like Kuka, Stapley, and ABB, but they are using very similar structure. As you see here, we have 3 first degree of freedom to reach to a point, which is positioning. The first one is here, out of space, out of plane again, and 2 rotational in a plane. And then we have a wrist at the wrist point. We have 3 degrees of freedom. These 3 degrees of freedom provide us with all the necessary orientation requirement that we have. Here we have 6 degrees of freedom in terms of actuation and 6 degrees of freedom in terms of the end effector. It can move to all the point, and it can have any orientation we want. We call it basically a general 6 degree of freedom manipulator that can be used in many, many applications. These kind of robots are used quite widely in many industrial applications. Of course, if we don't need to have all the 6 degree of freedom, we can reduce our design to 4 degree of freedom, 3 degree of freedom, or 5 degree of freedom to go to that specific application that we want. But these are some general design that can be used in many, many structures. So I hope that everything is clear from now. I appreciate if you quite interrupt me and ask question and provide me some feedback. Any question up to here?
Sir, excuse me.
Yes.
Is there any relation? I'm asking this question on page 14. Is there any relation between the controllable variable of our end effector and the number of actuator in spatial robots too? For example, like the one we had in planar robots.
Exactly.
Exactly.
How is that?
As a very good question, Hussein. Actually, what we have here, when we have, for example, 3 actuators or 3 joint space, I will discuss about it in more mathematical aspect in the next chapter. But when we have 3 degrees of freedom in terms of actuator, in terms of the joints, so it is quite clear that at the task space, at the end effector, we can only control 3 degrees of freedom motion. This motion could be x, y, z, it could be x, y, theta, or it could be theta 1, theta 2, theta 3. But it is only 3, since we have only 3 actuators here. So there is a one-to-one correspondence to this one. Of course, if the design is not good, maybe you put 3 degrees of freedom, 3 actuators there, but you cannot get all 3 workspace at the end effector. If the design is not good, we call it a singular composition or a singular configuration. If the robot is moving, you are actuating all 3 motors. You cannot have all 3 degrees of freedom from it. We can also put it back in another way. We can say that if we lock the motors, we have 3 motors, we lock them. Suppose that we break them. If we lock all of them, then the motion at the specific direction cannot move. For example, at x motion, if you see here, we have x, y, theta. If we lock all of them, then we cannot have any motion in x direction, any motion in y direction, and any motion in theta direction. This is the way we can go forward and backward, and we are using that in further analysis. Thank you, Hussein, for your good question. Please, I consider all of the students to contribute into the class, because with that, we have 2 benefits. First, I will go a bit slower, and you will have more time to learn more. And the second one, I get more energy from you and can teach a bit better. Now let's go through the... yes, please.
Could you explain again why Scara can be very fast?
Of course. Why Scara could be very fast? You see here, for example, compare this robot to this robot. As you see to this robot, if you want to move the arm, what is the application? The application is to pick something from one end. It is in packaging industries, as I showed you the movies. You would like to pick something and place it somewhere else. Pick somewhere and place it somewhere. At least see if the arms, the joints are not this direction, and it was this direction. If you want to move the weight of the joint, this link, we should compensate the weight to move it this way. But if you want to move it this way, perpendicular to the gravity, the weight is not important, because the weight is, compensated by the joint constraint. You have this direction here without any weight. If you just look at your hand, if you want to put it up, it is much harder than just put it this way. Isn't it like that? So if this is the case, so the power we would like to move here, there is no gravity there. There is only the acceleration that we can get, and we can put most of the power of the motors to accelerate the system. And to have the larger acceleration, we have faster speed and much less time in computations.
Thank you, sir.
Excuse me, Doctor.
Yes, please.
You said that it's not necessary at each joint we have to have an actuator.
Yes.
Okay. Say, for example, if we have three degree of freedom robot RRR system, and we have
I didn't say that. In serial manipulator, it is necessary to have all actuator in all joint. What I said, if you have a closed chain kinematic structure like what you have in this case, as you see here, you don't need to have
everywhere actuator. With one actuator, you can have one degree of motion. But if you have a serial manipulator and you don't have actuator at the point, so you lose the motion there. The actuation, the joint is not usable there. In serial manipulator, the number of joint and the number of actuators are the same.
Yes. In case of closed loop system,
Yeah.
we may have a less number of actuators.
Sure.
How much is the system is reliable or controllable, or how much we can determine its characteristics or its spatial characteristics?
The thing is, the number of actuator that you have will result in the number of degrees of freedom of the end effector. As you see here, we have only 1 degree of freedom, and we have only one motion here, one translational motion here. This is a one-to-one actuator here. We are using the structure to make the system quite stiff, not to add motion to the system. The category that you see here, in terms of the motion and the actuator, usually the number of joint, we call it the joint space. We call it furthermore in joint space. Please be a bit, calm right now. We have time to talk about this in further detail. But you see, the number of actuator gives you the number of controlled variable in the task space. So if you have 2 actuators, you can control only 2. And it is quite easy. If the design is good, we can have a one-to-one corresponding to that. But what does it mean to have a good design? Just conceptually, it should be mechanically sound. It should be very beautiful. No. Kinematically, we define how good is and how bad. Not only good and bad. The degree of goodness and badness is defined in chapter 4. Just a bit one-to-one. We can get to that in the future. Perfect. Now let's talk about the descriptions that we have. Very good to slow me down, but I have to move to rush because we have a lot of things to say, a lot of very interesting things to say. So we require to define the motion of a robot end effector, let's say, right now, or a quadrotor motor in a space, or a space shuttle in space. All of them should be defined by a number of degrees of freedom, translational, some of them in terms of orientation or rotational one. We start with a coordinate system. The most important thing is if we would like to describe the motion, we describe it into what coordinate system? Usually we use a Cartesian coordinate. Cartesian coordinate is x, y, z frame perpendicular to each other. You are all familiar with all in all your courses. This x, y, z coordinate, it is very important to have a reference frame. To what reference we are talking? And this reference frame should be fixed because otherwise the motion is relative. But fixed is somehow relative itself. As you know, really in the nature, there is no fixed point in the nature. The ancient people thought that Earth is fixed and the sun is rotating. Then they found that no, sun is fixed and Earth is rotating. Then they said, no, sun is also rotating in the spatial case. And there is no any real fixed point in the system. I don't want to go to the philosophical thing, but this is very important since when we call fixed in terms of, so if we are on the Earth and the robot is working in an industry, so we can consider Earth as fixed. But we need a fixed rotational frame because we would like to take the derivatives, the velocities, the acceleration, so everything should be considered from a fixed. Now, consider a fixed nearly fixed coordinate as A. Usually we use them x, y, z coordinate. So let me just give some notation. It is very important in robotics to have very good notations. So we have a frame, we call it a frame A, as you see. We put it in a bracket. Then this frame A has origin of frame A, we call it OA. It has x, y, z direction. We basically represent them with the unit vector as x, y, and z. As you see, the unit vector we had them to show that there are unit vectors in the space. And it's quite possible there is a moving object, as you see here. This moving object could be the end effector of the robot or anything, a quadcopter, a helicopter, a space shuttle, or anything that is moving in the space. And to represent the motion of this body, we should consider two things. First, we put a moving frame to that to have a mathematical description of the robot, of this object. This object could be quite like what I show, an apple or let's say a pear or something, could be quite volumetric, very beautiful, and smells good, and it's eatable or not. It is quite a piece of wood or steel. Doesn't matter how it is. Whatever this rigid body is, we consider it rigid body, we put another frame onto it to represent the motion. So instead of saying that how this object is moving, we consider how this basically frame, the moving or moving frame is moving. So we call it B usually. And usually, so it is an OB, it is put on some place. What place on the, what point on the rigid body we put it, it is quite arbitrary. You can put it there, but there are some references how we can put it on the center of mass or somewhere that it is symmetric point. But in any case, we call this XYZ here with UVW, small UVW, to represent it, to remind you that these are moving, they are not fixed. Of course, the fixed frame is also moving because the whole Earth and whole universe is moving, but considering to that, we can consider that this is quite fixed in terms of representation that we have, and this is moving with the object. And then we can have some sort of motion between these two. This motion could be a linear motion, could be an angular motion that we represent in the next slide. But who said that we should use coordinate system which is XYZ coordinate system or Cartesian coordinate space? It is not necessary always to use that, but we are more familiar with that. It is the most simplest one that we use. Somehow, when a robot is a cylindrical robot, it is moving in a cylinder. It is much easier to use cylindrical coordinate system. You have the knowledge of cylindrical coordinate in basic math courses that you have in the first semester of engineering courses. But usually in this course, we are not, or even using some spherical one. And it is interesting that if you design a spherical robot, like the robot that I show you for eye surgery last session, it is a spherical robot, so we can use a spherical coordinate as well. But if we are not specific on an application, usually we use Cartesian coordinate. And when we use Cartesian coordinate, there is some benefit, simple in the representation, simple, we are familiar with that, but maybe not the best or the beneficial one. Anyways, we have a frame A, OA, X, Y, Z frame. Let's go a bit further and see how we can define now the position of the system. We have a point on this rigid body. This point could be the point that a drill is acting in a robot, or we are painting, as you see, a point of interest. which is the robot is working with on that point, which is usually the end point of the end effector. We call this point P, and we can represent it very simple. As you see, again, we can have a P with 3 coordinate system. We can have this represented in the fixed point, so this gives us an absolute position of this point. We call it Px, Py, Pz as the component of this. You are familiar that we can, reflect this into 3 frames and have this one. And also I use a subscript, a left subscript here, a left superscript, a left superscript here, A, which means that we are considering this point relative to this frame. If we are considering it moving from where, if the frame is here, the base of the robot is here, how far it is from this base. So if we are considering another base here, this is much farther, and these components are different. So we consider the position P with respect to this frame in terms of its component Px, Py, and Pz. As I told you, superscript A represents the reference frame that we are putting in. Of course, this point P can be represented also moving frame. And if it is on the moving frame, so it is much easier because it is a point embedded in the system. We are considering from this position, this gives us a relative position, not an absolute position, a relative position. And usually this is fixed because if you move it in the space, this point is not moving with respect to this frame B. So we can have a frame P with respect to frame B quite different in terms of the size, in terms of the component, but they are both representing a position. The one of them is a relative position and the other one is absolute position. But the one which is important for us is the absolute position. So we are usually using this point with respect to a frame A, or we call it A, or we call it 0 frame. Usually in the next session, we have a 0 frame. 0 frame is basically the base frame or the fixed frame, either A frame, we maybe in some plane or aeroplane or motional plane, we call it I, inertial motion. We have an inertial frame, we call it frame I. It doesn't matter how we represent it, but consider that every vector P, any vector P can be represented in a frame with their components. Now, this is quite easy, but the second one is not as easy as the first one. How about the rotation? Consider that this rigid body has no relative motion, for example, no translational motion right now. Consider it is just moving. So it is moving around the point that we put the frame here. We had a frame here, now this motion is moving here, this way, and other ways around. Consider the orientation of the whole rigid body. This is very important. The first point is every single point on the rigid body has its own position vector. So this is point-wise. But all the orientation, every rigid body, all the points, everything in the rigid body has only one single orientation. All of them are rotating with each other. The point and the positions are different. So if you move, this point go to the left and this point go to the right. But when we are moving, in terms of orientation, in terms of the angle, all of them have the same angle or the same representation in terms of the angle. So angular motion, we consider it pure rotation for the whole rigid body. How to represent it? There are 400 times of representation, as I mentioned. There are many ways to represent that. I start with the most important and basic one. And this is our reference, not the simplest one. This is not very simple, not the first representations, where the Euler or some ancient people have produced. No, the most informative and most specific representation that we will use in future. We use basically the representation. Instead of using the motion of the rigid body with respect to a fixed frame, we call it the motion of a moving frame B with respect to a fixed frame V. We have only two frames now. Just forget about the rigid body, because the rigid body is just replaced by its moving frame, and the representation or the rotation between these two frames are given. So we have a fixed frame here. The robot or the rigid body has three frames here. Now it is moving. It is another frame here. As you see, the green one and the black one here, and these have some sort of representation. We call it this representation with the rotation matrix. And then we define the rotation matrix as, again, see here, everything is written here. We call the rotation matrix of frame B with respect to fixed frame A. How the motion, how the system has moved from position or state A to the B. We call a rotation matrix B with respect to A. What is the degrees, how much rotation we have. We don't put any angles here. We call it like this. We say that it is a matrix with 9 elements. This matrix has 3 rows, basically 3 columns. The first column is x hat of B with respect to A. X hat of B, it means that x hat of B means the U vector here. Consider the x of frame B. The x of frame B is U, the U hat, and it is a unitary vector. This unitary vector, there is a unitary vector in the space, has some component in x, y, and z, just represented it in x, y, and z. So it is R1, R11, R21, R31, the components of U with respect to frame x, y, z. And this is a unit vector. So if you put it here, the length of this vector should be 1. Otherwise, you have written it wrong. And again, the y, the V1, y hat B means the V. The y component of frame B is V. The V component in frame A, and again, the Z component in here. As you see, U, V, W, in frame A, you can have the UX, UY, UZ, VX, VY, VZ, and WX, WY, WZ. So this is somehow most general representation, but it needs 9 components. We know that if we have a general rotation in a space, we have only 3 components. We have 3 angles. Why we have 9 component here? It is just easier to manipulate, but much harder in terms of representation. And we show that although there are 9 components here, but 3 of them are independent. So there are some other aspect to it. Let me talk about a bit about rotation matrix. First wise, so if you consider it component wise, we can see that UX, U will, the same thing that I showed you here, XA and U hat, we call it here XB with respect to A is exactly the U, and U can be considered as UX, UY, UZ represented in the A frame. A, we call it IJK, the unit vector of that, and then we can consider this in here. But how we can easily find UX? Either by inspection, you can put the U here and find the components here, if you want to find this. But mathematically speaking, it is very easy to find UX. Anybody can help me to say how to find the component of U in X direction? We have a vector U, we have a vector X. The vector X in frame A is very simple.
1, 0, 0. 1, 0, 0 is a vector x. And we want to find the component ux here, either by composition and projection or using any response?
Dot product.
Dot product. Using dot product. If we dot product u with x, you see, u with x. If we could dot product u with x, it will give you the component u of x. So it is very easy to say that ux is the dot product of u with the x hat of a. So it is very easy in terms of rotation. xb dot x hat a, the dot product give you these two components. So if you have these three components, it is very easy to write to RB. Of course, this mathematical representation will help us to move around to give some detailed information about that. And this, as you see, this dot product, if we dot product two unit vectors, if we have two unit vectors and we dot product them, it gives the cosine angle between them. And so these are the cosine angle between D2, the u and x, u and y, and u and z. You see, u and y and u and z. And also the other component are the angle of v with x, y, and z, and the other one is w with x, y, and z. We call this representation somehow in many references, they call it direct cosine representation, but we call it a rotational. And I have done another very intelligent thing here as well. As you see here, we have the superscript everywhere. Just notice that robotic is the magic of notation. You should learn the notation. If you have the notation quite well, it is very easy to follow. As you see, we have a superscript here, but I intentionally left the superscript here. I didn't say that x hat b dot x hat a in a frame or in b frame or in c frame or in any frame. Why I didn't put it here? Because the dot product of two components is a scalar one. It doesn't matter in which frame you are representing these two. The only thing is that both of them should be represented in one single frame. So when I didn't put A here, this dot product can be calculated in frame A, in frame B, in frame C, or in any frame in the world. The dot product can be found in any cases. So again, ux, uy, uz is the rotation matrix or the dot products. Now, let's see some simple pure rotation. Some consider just a single simple pure rotation about x-axis with alpha. So we have an axis here. As you see, we are just omitting the rigid body now. It was a rigid body, but we don't forget the rigid body. We're just using the attached frame here. The UVW frame is moving about x-axis with the angle alpha. So we can easily find this component. So the u component is about exactly in x direction. So it is 1, 1, 1, 0, 0. You see, the component u is 1, 0, 0. And the component v, as you see, we have a cosine and a sine here, and there is no x. So x is 0. We have cosine and sine here. And the w is the projection of that, or perpendicular to that. So it is minus sine and cosine here. And you are very familiar with that. I'm sure that you have seen this in classical mechanics, that somehow the rotation matrix around x with alpha is like this. Cosine minus sine. And this one means that we are rotating around x with alpha angle. The y-axis is a bit different because we have a right-hand one. X and z are quite similar, but y is different. As you see the y,
we are moving around y, so y is 0, 1, 1, 0, 0. But as you see, instead of having cosine minus sign, we have cosine plus sign, and the sign comes here. This is because of the right-hand side angle that we have in gamma 1. So cosine, sine, and minus is in angular rotation around y-axis, and this z-axis is similar to the x rotation as we talked before. But what we can say that we have a rotation matrix, but this rotation matrix is a very, very interesting matrix. Very, very interesting matrix. It is not a simple matrix. It is not a very arbitrary matrix. It has different, although it has 9 components, only 3 of them are independent, as I mentioned before. We can see that through orthonormality or the matrix properties. This matrix is orthonormal. Orthonormal means that all the columns are orthogonal to each other. All the columns are normal or unit vectors. We saw that in the definition that these are unit vectors, as you see here. So the normal one is quite easy and understandable, but the orthogonality is also important. Yeah, it is quite easy since there is u v w, so u times u is always 1, v times v is always 1, w times w dot product is 1. This is the normal one. And u times v, they are orthogonal, 0. And this is because we are using the Cartesian coordinate. If we are using the Cartesian coordinate, they are perpendicular to each other. So u times v, v times w, and w times u are 0. As you see, we have 6 constraints here. Although the rotation matrix has 9 components, we have 6 interrelation component here. So it means that the rotation matrix has only 3 independent variables. And what are these 3 independent variables? We should see that. Look into that in terms of the physics and the conceptual understanding of that. Furthermore, we can see that u times v, since these are perpendicular, u cross v, not times. The cross product of u to v is giving u to w. And just note it that you have the right hand rotation. U to v gives you w, v to w gives you u, and w to u gives you v. And these are the cross product that we use the right hand side cross product to see. Always u times x, y, let's say x times y gives you the z axis. These are some further redundant relation that shows that the rotation matrix is particularly interesting. So we know in linear algebra that every orthonormal matrix, the transposition of the matrix is equal to the basically to the inverse of it. The inverse and transposition for an orthonormal matrix is the same. But here we don't have just a mathematical matrix. We have a matrix that has the concept of rotation in it. We call it when we have R B with respect to A, when we transpose it, this is R B with respect to A. When we transpose it, we are having like this. You see? And this will give you the RA with respect to B. This means that basically, if you are, instead of moving from position A to position B, if you are in a position A or in a state A, then you have in a state B, the rotation from A to B is represented with RB with respect to A. But if you inverse the rotation, Consider just physically, instead of moving that way, moving backward. You are in the frame B and then moving to frame A. It is not necessary to find the inverse. The transposition is always the inverse. And you see the inverse is the transposition. This is always true for all orthonormal matrices. But in here, it has some physical insight into it. So these are two very important issues. And the second one, which is the fourth property, which is very, very important, is not only this rotation matrix gives you the rotation action, or you can find a mapping for pure rotational map. Consider that you have, in a rigid body, you have a point in this rigid body, we call it P with respect to A. And then we move this frame A to frame B. We rotate it, just pure rotation mapping. Consider pure rotation. We don't have any translation right now. We have only pure mapping. Now, this point P goes to somewhere else, call it P2 or PB. We call it P with respect to A, P with respect to B, where B is rotated version of the frame A. We can see that if we would like to change the coordinate from B to A, if we would like to represent P with respect to B, represented into frame A, it is very easy to just multiply it with RAB. Consider, just canceling the subscript and superscript of here, P with respect to B. If it is left multiplied with a matrix, with a special matrix, which is R, B with respect to A, it gives you the P with respect to A. The proof is given in the book. I would like to inform you, for sure, you should follow the books, and I will give you, this is the fourth reference book, the Pararobot book, which is available on the website LMS system that I showed you. So, for example, consider that we have a rotation matrix, some rotation matrix which is an angle here. As you see, this rotation matrix is very good because these are, if you look at them, they have all unit vectors. The norm of these columns are all 1, and you can check that if you multiply these two together, gives you the second one, and this is the way a rotation matrix is. How it is found, this is not a matter of question here, but consider that on this rigid body, on the frame B, when we say on the frame B, we have a moving platform, so we can everywhere in the space that it's moving, the point B has a fixed vector position with respect to the moving frame. So if we consider that, and we have a rotation here, then we have a rotation, we use this rotation to find P with respect to A. This is 2 minus 1, 0. This goes to 1.93, 1.07, and this. It is quite, all the components change, but it is very interesting to see that norm of this vector is square root of 5. Norm of this vector, just calculate it, is also square root of 5. A vector here has moved to another vector. A representation here has moved to another representation there without changing the size. And this is quite expectable from the mapping that we are doing. Rotation mapping just rotates the vectors, doesn't magnifies or decrease the size of the vector. So you see that this shows you physically that this vector is a rotation version of this. It has the same inheritance of the length of this vector, but just change in the direction. So we can have this pure rotation map here. This is very important since we are using some sort of mapping in here. Let me just go to another version, and I'm finalizing this session, but with these two guys. So if this is a map, if rotation is a map, now consider it control in a control version. So we have a map. So the map can be represented with the induced norm, or how this map will change the vectors. As you will see here in this example, doesn't change the length, it just changes the angle of the vector. So we can consider that with the determinant, which is some sort of the norm of the vector. Not only the rows and vectors of the orthonormals have a very specific issue, the determinant has also very, very specific value. The determinant of this any rotation matrix is 1. So it means that it doesn't change the length of the vector. Norm of the vector on the pure rotational map is preserved. And this is the how one of the proof. You can have different type of proofs here that for any rotational matrix, the determinant is 1. Wow, this is the best part of this section. What about the eigenvalues and the eigenvectors? If a system has a determinant of a rotation matrix is 1, most of you are control student. When the determinant of a matrix is 1, it means that the multiplication or of the eigenvalues should be all equal to 1. So that doesn't mean that all the eigenvalues of this matrix is 1? No. It means that it has 3 eigenvalues. 3 eigenvalues. One of them is 1. 2 other ones are complex conjugate, e to power plus I theta, e to power minus I theta, e plus minus I theta, or j theta. Cosine of theta plus minus j sine of theta. You know that from pure math. They are not all 1, but the norm of them are all 1. You know that e to power I theta is the norm of it. The absolute value of that is 1. So here you see that the determinant is 1. Here you see that the eigenvectors are also all, the length of the eigenvectors are 1. But one of them is real. 2 other ones are complex. Should be complex. It is only not complex if theta is 0. There is no rotation. And this theta, the most important one, is this theta. Theta is an angle. In an angle in the space, and it can be found quite easily, the eigenvalues of a rotation matrix, you can find it from linear algebra. From this, a trace of the matrix minus 1 divided by 2 gives you the cosine of the theta. So the trace minus 1 divided by 2, very easy. Trace minus 1 divided by 2. This gives you the cosine of the theta. It gives you an angle. And this angle, I claim this is an angle of rotation in space. One single angle in the rotation. As you see here, if we have moving a frame, instead of considering a Cartesian one and, x, y, z, basically it is moving about a vector with an angle alpha, with an angle theta. But what is this vector? Where is this vector? The eigenvalues gives you the angle of rotation. But what gives you the vector of rotation? The vector that about is the rotation is
taking place? Everybody is quite quiet.
Maybe eigenvectors.
Not eigenvectors, the real eigenvector. Since it has 3 eigenvalues, one of them real, 2 of them complex, it has 3 eigenvectors. One of them real, 2 of them complex. The complex one has a very beautiful meaning I don't want to describe here, but there is one eigenvector, we call it S. One real eigenvector. This gives you the real eigenvector gives you the axis of rotation. Of course, for now I'm just claiming that this theta is the angle of rotation, and this vector is the angle vector of that about it the rotation is taking place. Let me stop here. I would like you to think of it. I will prove this claim in next session. Thank you for being with us. If there is any question, don't hesitate to contact me. Ali, please.
سلام دکتر. ببخشید من فارسی صحبت میکنم. اول
عزیزم
ببینم سوال کسی میپرسه. بعد گفتم یه سوالی بپرسم که شاید سوال خوبی نباشه، یعنی بیشتر میتونه بچه‌ها رو گیج کنه.
نکن این کارو، گیجشون نکن. حالا بپرس، اگه گیجشون کرد من جواب نمیدم. بپرس.
تو بعضی نرم افزارها مثلا من برخورد داشتم، البته ببخشید من فارسی صحبت میکنم، اگه شما به هر زبانی دوست داشتید جواب بدید. بعضی نرم افزارها مثلا من برخورد داشتم مایا یا سرچ کردم مثلا دایرکتیکس، اینا از دستگاه مختصات راستگرد استفاده نمیکنن، از دستگاه مختصات چپگرد استفاده میکنن. خب الان تمامی تعریفایی که شما الان ذکر کردید برای توصیف دوران یه جسم در دستگاه مختصات فضایی، من نگاه کردم اینا مختصات دستگاه کارتزیان راستگرده.
همینجوری.
بعد این دستگاه مختصات بشه چپگرد چه اتفاقی میفته و اینکه چقدر این فرمول عوض میشه. وقتی میگم فرمول عوض میشه منظورم اسلاید بعدی هم هست که همین فرمول مثلا ماتریس دوران چه فرق میکنه یا زاویه اولر و بقیه مواضع. ببخشید اگه فارسی گفتم.
The question was that if we don't use a right hand Cartesian coordinate, if we use a left hand Cartesian coordinate, what happened to the system? What happened to these definitions? What happened to the matrix too? Of course, everything should be designed from it. Many issues will be changing. But, Ali John, the important thing is the angle of rotation and the vector of rotation, which we call a screw axis. These are inherent with the motion. This doesn't change. Many things will change. Almost everything will change. But the inheritance, something which is quite embedded with the system, which is this angle and this vector, angle of rotation and vector of rotation doesn't change. Yes, there is another question. Please, feel free to speak in Farsi. Don't worry. یعنی راحت باشین بچه‌ها.
Excuse me, doctor.
Oh, you are Hussein. Please.
Yes, in slide 23, 2 slides before. From a physical point, I have a question. From a physical point of view, considering time, it's represented by we have point P1 at time t0 was rotated to point P2 at time t1. This rotation is presented by this matrix.
Did I talk anything about time? Hussein?
No.
Why you are adding time to it?
I'm trying to understand. Okay.
Why you are putting time? There is no time here.
Okay.
Especially, especially for Ali and Hossein, both of you, be quite easy to understand. No, I didn't say any time here. I said there is one position here, one position there. What happened in between? There is another issue. I will talk about it later. But right now, there is only pure rotational mapping.
Pure rotational presentation. Yes.
Yeah, that's it.
Okay.
Perfect. Any other questions?
Excuse me, what is the application of the mechanism in slide 10?
It is very beautiful. Look at it could be, a mixing mechanism.
Okay.
I didn't talk about the application in this session. I talked a lot about the application in the previous session. But I like it very much, it is quite easy. Perfect. Thank you very much, everybody. We are out of time. I will be in the next hour, my office time. If there is any other question, I will be more than happy to have you. We have 27 people in the class. The class only is registered with maybe 16 people. I don't know how many people are attending this class. Please add the credential file I showed you before and try to register if you would like to attend this class, because what we are talking is not just the movies and these beautiful things. These are the background. The foreground is the mathematics and the physics and the representation that needs some sort of training and entertainment with the training. So you should follow the course quite with the exams, with the assignment and everything. Perfect. Thank you very much and goodbye.
Professor, would you please put registration Google Doc link in the chat?
It is on the home page of the site. I will put it in the chat, but everything is available on the site. So if you access to the site, you can have it.
I don't have access to the site.
No, the site of the course.
Okay, thanks a lot.
It is available to everybody. This is available to everybody. I will put it here. I will show you just to see where it is. I hope it is working, my internet. You go to my site. Easily just search Google Taghirad and you can find robotic course here. Oh, we are out of time. And in robotic course, here there is the classroom. Just everybody, we are using the Skype for now because I want to show you some movies. But the main classroom link is here. I will put on the side. And then also here, you see the credential here. If you click here, you find the robotic class list. We have only 15 up to now here. Please add your name into this class list. Thank you very much and take care of yourself.
خداحافظ.
خداحافظ.
Doctor? If I have a personal question after 5 minutes?
Yes, please.
Yes.
Come to the session, the next session.
Okay.
Yeah.